So I'll be speaking today about some of my research, and this is research I've been doing for the past several years, and I study volcanoes. Volcanoes are pretty cool. They are big, they're beautiful, as this picture of Santa Maria volcano or Sant'Igito Dome shows. Spectacular ballistic tracks of incandescent blocks taken about a month or so ago. You can even see one here that flew through the air and then bounced. And volcanoes, so they're beautiful features, they're amazing features, and they're geologically important. Volcanoes generate marker horizons that our geologists use and anthropologists use. And volcanoes are also very important from a hazard standpoint. These features, unfortunately, can cause devastation at a local scale through pyroclastic flows or lava flows or mud flows, and also at a regional or global scale through ash and ash put into the atmosphere and aviation hazards. So understanding volcanoes is quite important. And I go about this in a couple different ways. The most obvious way is to go to a volcano and watch one. So make direct observations, such as the Sant'Igito lava dome. These are time-lapse images taken about a month and a half ago, and we can see the dome. We can see the dome flowing in this direction here. The clouds rolled in. It happens frequently at volcanoes. The dome flowing along like this at speeds of about 2 or 3 meters per hour. There's this region, central region, probably above the conduit, where it's breathing, and we can couple these observations with seismic information, other geophysical signals, and we can make some inferences about what's controlling the volcanic processes and about what does this mean to see this sort of breathing feature here in the center. How can we use that to interpret seismic signals, or flipped around the other way, how can we use seismic signals to interpret dome eruptions or interpret how lava flows are moving? But for a lot of processes at volcanoes, we don't have a way of actually seeing what's going on. This beautiful picture of Redoubt Volcano taken about 22 years ago shows a lovely mountain right here, and rising up is this big buoyant ash plume, rising up to a height of about 12 or 14 kilometers, right where airplanes fly. In fact, this plume almost shot down a 747. But there's a lot going on here that we can't see. Specifically, we can draw pretty cartoons like this, where we see some body of magma down at depth, and it's probably not this big magma cave that I just drew here. And it's connected by some pipe or some conduit up to the surface, and we can never see either one of those. Geologists draw all these lovely pictures, and that's what we draw a picture of, but we don't really know that it looks like that. We have to use some other way of studying this and seeing this, because we cannot directly observe it. Similarly, you may notice that here's the top of the volcano, but the plume is rising up from several kilometers further over to the north. So this buoyant plume is not sourced by the top of the mountain. Instead, it's coming off the pyroclastic flow over here. And pyroclastic flows, such as this picture here from Unzen volcano, are big, hot, fast, nasty things. They travel at about 100 miles per hour. They're several hundred degrees in temperature. They're hundreds of meters thick. They're really bad. And we have no way of directly seeing what's inside of them. And in fact, you don't really want to be anywhere near one of these when it's happening. So how can we study these pyroclastic flows and this magma if we can't actually look inside of them? Well, one way is through experiments. So down 2 floors from here, over in the Mineral Sciences Department, we have an experimental petrology lab. And in this lab, we can make very small batches of magma. And so I can look at a rock, in this case from El Chichon, and I can see that this rock contains amphibole crystals, clinopyroxene crystals, plagioclase crystals, and various other minerals. And then I can put samples of magma in, or samples of rock in at different conditions, such as 825 degrees C and 100 megapascals, or 1,000 atmospheres pressure. And I can put in different batches of magma at different conditions, and I can see how that magma crystallizes, or how that magma changes as a function of pressure and temperature. And therefore I can map out and see how hot was this magma before it erupted, what pressure was it at, and therefore essentially get a window on this magma system, even though we can never actually go there. In the case of El Chichon, it turns out the magma is stored right about here, which is conveniently where we did not run an experiment. That frequently happens. The other way, another thing we can look at are these pyroclastic flows. So these are some laboratory experiments, and in this case here, we can see a movie of a tank that's about 20 feet long, and we can see this current here that's moving along, and then lifts off, and even at a certain point it starts to flow backwards. Thanks. Now, in the case of natural pyroclastic flows, you may remember that I said they're traveling at something like 100 miles per hour. They're hundreds of meters thick and hundreds of degrees. This guy is traveling at about 10 centimeters per second, is about 10 or 20 centimeters thick, and about 2 degrees. So it's really not going to ruin your day. We can see inside of this thing because it's only about 2 feet across. We can make all sorts of measurements, and so we can actually link the behavior in the current up here with the behavior of turbulent structures, which are mapped out right here. And we can also track the sedimentation coming from this. So this allows us to link experiments that we can run in a lab to natural currents and the deposits of natural currents. So to wrap this all up then, we have quite a bit of exciting volcanology research going on here. We have ongoing fieldwork in Hawaii, Guatemala, and Kamchatka. We have petrological studies of magma conditions conducted in the experimental lab downstairs, and lots more exciting things, so stay tuned.
What's the biggest volcanic eruption known of all time? When did it occur, and what was its effect?
The question is, what is the biggest volcanic eruption of all time? When did it occur, and what was its effect? The biggest one I can the biggest one off the top of my head is the Fish Canyon Tuff eruption, and I actually forget when it was, but it was something like about 10,000 cubic kilometers of magma, which for perspective, that's about 100,000 times bigger than Mount St. Helens. So it's a very big eruption. Eruptions of that scale tend to totally alter, well, we would imagine that they totally alter what's going on, at least in that hemisphere. So when Yellowstone erupted at 600,000 years ago, there's centimeters of ash from that eruption in Texas and other places. So that gives you a sense that this would really change things. It would probably change global climate, or at least that hemisphere of climate for several years or decades.